I'm Pranay Kaul, and I will present our work titled Label, Verify, Correct, a simple few-shot object detection method, in collaboration with Wade G. and Andrew Zisserman.
In recent years, there has been impressive success in object detection, achieved through strong supervision with abundant annotation labels. However, this can be difficult to collect for all classes of interest. Hence, the aim of this work is to expand an existing object detector for new categories given only a few labeled instances.
We start with a detector trained with exhaustive data for a limited set of base categories. For each novel category, we are only given K annotations. There are two key challenges. First, the extreme imbalance between the annotations for base and novel categories in the large image dataset. Second, most novel instances are unlabeled. That is, they are treated as background. The outcome is few-shot object detectors are severely biased against detecting novel category instances. Our solutions are to first improve the training and use augmentations to alleviate this bias. Second, use pseudo-labeling to give abundant annotations for novel categories and remove this bias.
Now we shall take a closer look at the challenges. We start from the detector of a previous work based on FASTA RCNN, containing a region proposal network and region of interest classification. We note that many easy novel instances are not recalled by the RPN. Our solution is simply to fine-tune the RPN-specific parameters on the limited novel instances. This drastically improves recall of novel instances, largely bridging the gap to the ideal RPN performance from traditional object detection. Onto region of interest classification. If we follow previous work but use all novel annotations in the dataset as an oracle test of the method's upper bound, we find the performance is still poor. The features learned are heavily biased against novel instances, even when a suitable proposal is present. By fine-tuning the ROI and RPN heads on limited novel data instead of just the final layer, plus adding augmentations, we can correctly classify additional novel instances and bridge the gap to the performance achieved from our oracle test. After making use of the simple improvements detailed previously, we have an initial detector. Our work uses this detector for pseudo-labeling. Naively pseudo-labeling is suboptimal, containing many false positives, so we make use of a novel pseudo-labeling process with 3 steps. After this process, we have thousands of pseudo-annotations for novel instances and use them to retrain our initial detector end to end. Delving into details of our pseudo-labeling method, we start with candidate sourcing. To obtain a list of novel detections, we simply perform inference using our initial detector on all training images. However, this list is very noisy, containing many false positives. To reduce the size of this list, we only keep detections with a confidence score greater than 0.8. Each element of this reduced list is called a candidate. For the second step, label verification, we use the given few-shot annotations as training samples to construct a nearest neighbors classifier, making use of strong Dino self-supervised features from a vision transformer. To perform label verification, we pass all candidates to the constructed classifier using the same self-supervised features. A candidate is accepted or verified only if our nearest neighbor classifier predicts the same novel class as the initial detector. Here are qualitative examples of label verification. The candidates on top are verified because the detector and nearest neighbor classes match. The candidates at the bottom are rejected because they do not. Many of the verified candidates from the previous step still have suboptimal bounding box annotations. The third and final step, box correction, solves this. A box corrector model inspired by Cascade RCNN is trained in a class-agnostic manner using available ground truth annotation. This box corrector takes the image and box from a verified candidate as input and outputs a corrected box. The corrected box and the class label from label verification are combined to form our pseudo-annotations. After our 3-step pseudo-labeling process, we have thousands of novel pseudo-annotations of previously unlabeled instances. We use these and the abundant ground truth data for base annotations to retrain our detector end to end. Here are some box correction examples. The initial bounding box is shown in blue and the improved bounding box is shown in green. We outperformed the previous state-of-the-art method on the Microsoft Cocoa few-shot object detection benchmark. For each novel category, 10 or 30 annotations are given. Here we can see the improvement in the precision recall curves after pseudo-labeling on the 30-shot Cocoa benchmark. We also outperformed the previous state-of-the-art in almost all cases for the Pascal VOC benchmark. Please see our project website for further information.